In this lesson, we will explore the concept of radicals and rational expressions and how to convert between radicals and exponential form. Now, with that in mind, let's look at what is a radical. Now, radical is a square, a cube, or a higher root, such as the square root of 25. Now, we've seen that all like many times over, but what we didn't realize that in that riddle radical sign, there's actually a number 2 up front. Now, when we try to figure out the square root of 2, we have to think of a number multiplied by itself twice to give us 25. And we know that that is 5. So the square root of 25 is 5. But not always are we going to be looking at the square root. We're going to look at the cube root, the fourth root, the fifth root, the sixth root. So that's going to change for us. Now, if we're looking at the cubed root of 27, we have to think of a number multiplied by itself 3 times to give us 27. So that would be something like 3 times 3, which is 9. 9 times 3 is 27. So the cubed root of 27 would be 3. And now if we look at the fourth root of 16, we have to think of a number multiplied by itself 4 times to result in the number 16. So that would be 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. So the fourth root of 16 would be 2. Now let's look at the different parts of a radical. So that number that with the square root of 25, it's actually 2. That's known as the index, or that root. Okay. Then we have the radical sign or symbol. And the number underneath the radical sign is called the radicand. A radical can be expressed in 2 ways, whether exact answer, square root of 5 there, or the approximate answer, if we put that into our calculators, would be 2.36 dot, dot, dot. And we can have an entire radical, which is a radical with the coefficient of 1. Again, if we don't see it there, we know it's there. A mixed radical is a radical with coefficient other than 1. So an example there is 2 root 3. Like radicals are radicals with the same radicand. So again, that's really critical when we go to add and subtract radicals. You do have to have like radicals, meaning the radical with the same radicand. So 2 root 5 and 4 root 5 are the same, are like radicals. They have the same radical value of root 5. The coefficient out front are different, and that's okay. Radical rules. So this only applies, of course, when A is greater than or equal to 0 or B is greater than or equal to 0, meaning that the radicand is a positive value. Now, the product rule radicals tells us if we have taking the radical, the square root in this case of a product, you can break that down into root A times root B. So in this case, this would be root 5 times root 2. So you can break that down. The quotient rule of radicands tells us the same thing. You can break that down. So that would be root 2 over root 3. Okay, square root of a square root rule. So that just tells me is if we're multiplying root 7 times root 7, that is the same thing as 7 to the power of 2. And I want you to just remind yourselves that we said there's a number 2 as that index value that we just never paid attention to. If you take the radical square of a square root rule, that means those two cancel out and the value would be 7. So keep that in mind. The index and the exponent are the same. You're left with that radicand of 7. And that actually applies to what we see up here. If I'm just going to, sorry, not to make you dizzy, but root 25 was 5 to the power of 2. Those cancel out and you're left with 5. Same thing here. 3 to the power of 3. Those cancel out and you're left with 3. Same thing here. Those root and exponents are the same, so you're left with 2. Just want to bring that to your attention because, again, if we can pick up on that, then these rules will come in and work smoother. So key concept, an entire radical can be simplified to a mixed radical in simplest form by removing the largest perfect square, cube, etc. from under the radical to form a simplified mixed radical. Express each radical as a simplified mixed radical. So what does that mean? So you really want to try to remind yourself of all the perfect squares. And then when I say perfect squares, that would be something like 4, because 2 times 2 is 4. 9, because 3 times 3 is 9. 16, because 4 times 4 is 16. Okay, so you want to break down the radical as a mixed radical where one of the radicals radicand is a perfect square. So 8, we can do that. So with 8, we can say that would be the same thing as root 4 times root 2, because 4 times 2 is 8. So we just broke it down into two separate radicals because we can simplify this. What is the square root of 4? Well, the square root of 4 is 2. So this could be simplified to 2 root 2. Huh? 50, same idea. Think of a perfect square that is a factor of 50. So we know that that can be broken down into 25 times root 2. Well, we can simplify. The square root of 25 we know is 5, so this becomes 5 root 2. Okay. So sometimes we're already starting with a mixed. So we're going to take 3. We know that would be 25 times 3. Notice we're just expressing it as a product using the product rule of radicals so that we can fully simplify, because we know the square root of 25 is 5. So this becomes 3 times 5 times root 3. Well, 3 times 5 is 15. Okay, same thing here. We can use that quotient rule of radicals. This would be the square root of 1 over the square root of 4. You can break that down because we can simplify. The square root of 1 is 1. The square root of 4 is 2. Okay. Like radicals can be combined through addition and subtraction of their coefficient. So like radicals, just like terms, you must have like radicals in order to add or subtract radicals. So in this example, we have simplified the following radicals. So 3 radicals 7 plus 2 radicals 7. Okay, notice the radicands are exactly the same. So these are considered like radicals. So you would keep the radical and then add those coefficients. So in this case, this would become, and I'm going to show the adding. You don't have to show that, but 3 plus 2, because we're adding those coefficients, and we can. 3 plus 2 we know is 5. So 5 radical 7. Okay, so in B, it's not that obvious. We always want to simplify in our lowest terms. So let's see if we can express the radical 300 in mixed form. So thinking of a perfect square, that would be a factor of 300. 100 comes to mind for me. So we're going to say, I'm going to break that down as a product of 100 times radical 3 minus, again, that would be radical 9, because 9 times 3 is 27. Okay, so with that in mind, we can take the square root of 100, which is 10, and the square root of 9, which is 3. Notice now we've created like radicals. Again, we keep the radicand, the radical, and because those like radicals, but we simplify the coefficient. So 10 minus 3, which would be 7 root or radical 3. Okay, so adding 3. So again, we always want to, because looking as it is now, none of those radicals are the same. They're not like radicals because the radicands are all separate, different numbers. But we can break those radicands down to create like radicals. So again, we need to be strong on our, we know 4 times 3, 4 is a perfect square. Now looking at 48, we know that 16 times 3 is 48. So we're going to take 16 and 3, and 75 would be 25 times 3. Okay, so if we take the square root of 4, we know is 2, so this becomes 5 times 2 root radical 3, 2, 4 radical 3, plus 7 times 5 radical 3. Fully simplify first before adding or subtracting like radicals. So 5 times 2 we know is 10 minus 8 plus 35. Okay, so notice now we have like radicals. So if we could take 10 minus 8, which is 2, plus 35, which would be 37 radical 3. Okay. Also, radicals can be multiplied using the distributive property and the FOIL method. Simplify the following radicals. So again, what is outside the bracket, we multiply with everything inside the bracket. So we have 3 radical 3. We're going to multiply that by 5 radical 2. And then going to multiply that by just 2. Now, when we're multiplying radicals, the coefficients get multiplied together and the radicands get multiplied together, meaning the number underneath um, the radical sign. So in this case, we would take 3 times 5 would get multiplied together, 15, and then we take 3 times 2, which is 6. Okay, notice the second term in the bracket does not have a radical attached to it, so we can only multiply those coefficients. So this becomes 6 radical 3, because 3 times 2 is 6, and of course that radical becomes attached. Now there's nothing else we can do here. Remember, you can only add or subtract like radicals. Radical 3 and radical 3 and radical 6 are not like radicals. Okay? Again, distribute properly. Again, coefficients get multiplied together, radicals get multiplied together, meaning those radicand values can only be multiplied by each other. Okay, coefficients get multiplied, radicands get multiplied by each other. Now, if there's nothing up front, we know it's a 1. So negative 2 times 1, which is negative 2, root 3 times 5, which is 15, negative 2 times positive 3, which is negative 6, 7 times 3, which is 21. Okay. So again, there's nothing here that we can um, simplify because 15, there's no factor there that we can express 15 with a perfect square. Likewise, 21. Okay. Now, C is a binomial square, so we can use the shortcut. We know when we have a binomial square, we square the first term. Remind you if this is a binomial square. 2 times the 2 terms multiply together, so root 5 times root 6 plus root 6 squared. Squared. Okay, so root 5 to the power of 2. Remember, those would just cancel out, so we're left with 5 plus those radicals get multiplied to root 5 times 6, which is 30 plus 6. So 5 plus 6 we can simplify, so this becomes 11 plus 2 root 30. Because these are like terms. There we have it. Okay, moving on, we're going to look at radicals and rational exponents. Okay, a term, number, or variable raised to a rational exponent is equivalent to a radical. Okay, so a2, the exponent of 1 over m, is equal to the mth root of a. So the rational exponent 1 over m indicates the mth root of the base. Note, m has to be greater than 1. M is an element of natural numbers, and a cannot equal to 0. Okay, so notice this is our root slash index value. Okay, so the exponent, because the exponent is a rational, so that means a fraction. The denominator represents that root of your radical. So with that in mind here, we identify that 2 is the root. Okay, so this would be the second root of 4 as a radical. Well, we know if we take the square root or the second root of 4, 2 to the power of 2 is 4, which would be just 2. Okay, if you want to show that, we know that it's 2 to the power of 2, and those cancel out, and we're left with 2. Okay, so here we notice that the exponent is 1 over 3, so that rational exponent, so that fraction where the denominator is 3, which that would represent the root, slash our index in our radical. So this would be the third of 125. Again, if you want to just use that practice, 1 multiplied by itself 3 times gives you 125. Well, that would be 5 to the power of 3. Again, those cancel out, and we're left with 5. So the third root of 125 is 5. Okay, fourth root of 81. Okay, what multiplied by itself 4 times gives you 81. That would be 3 to the power of 4. Those cancel out, and you're left with 3. Excellent. If, however, the numerator of a rational exponent is not 1, so those examples before, that means the numerator in that exponent, that's a fraction. If it's not 1, m and n are considered positive integers, then we can say a to the exponent of m over n is equal to, so you can express it a to the power of n all to the exponent of 1 over n, or a to the exponent of 1 over n all to the exponent of m. So what that means is we still know that the denominator of that rational exponent is the root or the index, but 2 represents the exponent. Okay, so in this case, we would say 729 is equal to, we want to figure out the third root of 729, and that's all going to be to the exponent of 2. Okay, so the third root of 729, what multiplied by itself 3 times to give you 729? Well, that's going to be 9. Well, we know those are going to cancel out, so we're left with 9 to the power of 2, which is equal to 81. Excellent. Let's evaluate the following then. Again, I always like to identify, just because we're going through this the first time, this third is the root, 1 would be your exponent. Okay, so keep that in mind. Now, again, when it's 1, we don't have to worry about that. We don't have to show that work because anything to the power of 1 is 1. But I'm going to let you see that it's going to be the third root of 27 all to the power of 1. I'm just going to write in there just to get into that practice. Now, what multiplied by itself 3 times gives you 27? That would be 3 to the power of 3, all to the power of 1. Those cancel out, and you're left with 3 to the power of 1, which is 3. I'm just getting to that practice. So we know 3 is my root, 2 is my exponent. So we're going to say the third root of 64, all to the power of 2. Okay, so what multiplied by itself 3 times gives you 64? We know that's going to be 4. Okay, so those cancel out, and we're left with 4 to the power of 2, 4 to the power of 2, which is 16. Okay, again, this is my root of 2, and then we have the exponent of 3. So we're going to take the square root, or the 16 over 25, all to the power of 3. Now, again, some of you are like, Miss, I don't need to express that. That's fine. We know the square root of 16 is 4, 4 squared. Square root of 25 is 5, because 5 squared is 25, all to the power of 3. What you do want to remember, though, you have to distribute that properly. So it becomes 4 to the power of 3 over 5 to the power of 3. Well, again, exponents are repeated multiplication, so 4 times 4 times 4, which we know is 64, and 5 times 5 times 5, which is 125. Okay, this applies to when you're dealing with variables as well. So keep in mind that, as I've always stressed, if you don't see an exponent, even with the numerical coefficient, it has an exponent of 1. If it's in the brackets to an exponent, you do have to share that. Okay, so keep that in mind. Must, must, must. So with that in mind, we're going to take 1/3 times 1/3 here. So it's going to be 343 to the power of 1/3, x to the power of 1/3 times 3, which we can just say is 1. Is 3 times 1/3 would be 3 over 3, which is simply 1. Then we can take the cubed root, the third root of 343, x. Well, we know the cubed roots, what is multiplied by itself 3 times to give you 343? That would be 7. So this becomes 7x. Okay, same idea. What gets overlooked a lot of times, you have to make sure that you distribute to all the exponents. So each of those bases of an exponent. So 27 to the exponent of 1. So this becomes 27 to the 2/3, 8 to the power of 3 times 2/3, which would be 2. On this, oh, let me just write it in. I think it looks a little bit, I'm going to just do it a little bit differently here. We're going to say 3 times 2/3 and b to the power of 6 times 2/3. So this becomes the third root of 27, all to the power of 2, a to the power of. So 3 times 2, numerator number 6, divided by 3, which is 2, and b to the power of 6 times 2 is 12, 12 divided by 3, which is 4. Taking the third root of 27, we know that's going to be 3, because 3 times 3 is 9, 9 times 3 is 27. And then we know 3 squared is 9. So it's 9a squared, b to the power of 4. All right, so let's approach this a little bit differently and just jump right into the fact that this is, I expanded above using my exponent rules. I'm going to show this as a root of 3, exponent of 2, just to show that different ways of approaching similar type questions. So we can take the third root of 8x cubed, 125, and then we're going to take that all to the power of 2. Okay, so third root. So thinking of a number multiplied by itself twice, we're going to say that is, sorry, not twice, 3 times. That's going to be 2. So we're going to say 2x all over 5. That's all to the power of 3. Right? Because x to the power of 3, 2 to the power of 8, and 5 to the power of 3 is, and then we're going to say all to the power of 2. Okay, so by doing that, we've expressed the radicand as a base to the power of 3. 2 to the power of 3 is 8. X to the power of 3 is x cubed. 5 to the power of 3 is 125. By doing that, we've now simplified, and those cancel out, and we're left with 2x over 5 all to the power of 2. And don't forget those exponents, so it becomes 2 to the power of 1 times 2, which is 2, x to the power of 2, and then 5 to the power of 2. So we have 2 squared is equal to 4, x to the power of 2, all over 5 squared, which is 25. Okay, last but not least, again, we have a negative exponent. So to make that negative exponent positive, we take its reciprocal. So I would do that first. So this would become 81y to the power of 8 all over 16, all to the power of 3 over 4. Okay, so then in this case, we would be taking the fourth root of 81y8 all over 16, and then we're going to take it to the power of 3. So don't forget that. This is always my root. This is my exponent. Notice nothing happened to the rational exponent other than from negative went from positive when we took the reciprocal. Now, thinking of what multiplied by itself 4 times would give me 81. Well, that would be 3. What multiplied by itself 4 times would give me y to the power of 8. Well, that would be y to the power of 2. 16, what multiplied by itself 4 times would give me 16. That would be 2. So that's 2 all to the power of 4, and you're taking the fourth root of all that, all to the power of 3. Now again, by doing that, these cancel out, and you're left with that radicand of 3y squared all over 2 all to the power of 3. So this would become 3 to the power of 3, y to the power of 6, and 2 to the power of 3. Simplified, 3 to the power of 3, which is 27, y to the power of 6, all over 2 to the power of 3, which is